Hello and welcome back to part 4 of our reusable rocketry course. So in this part we'll be looking at reusable systems, what they are, how they work, but mostly we'll be asking two big questions. Why would you reuse a rocket and how do you reuse a rocket? Well, why is the easy part, because all of the rockets we've looked at before in the last part, their first stages, once they've detached, they just crash back to Earth in the ocean or in the water. And these are some of the most advanced pieces of hardware on the planet. Rocket engines are not only complex, but they're also ludicrously expensive. And dropping them into the ocean each time is like loading a jet plane up with passengers, flying it to the other side of the world, and then crashing it once you land. It's just throwing away resources. And the reason that nobody's done these reusable rockets before is because it was thought almost impossible. A notoriously difficult task. Because getting the rocket up there is easy, and then usually you just let it crash down into the water or into the land again. But getting it back down in one piece and able for it to be reused again is remarkably more difficult. So in this part we're going to be looking at two different ways that you can reuse a rocket. Like, how can you take something that's just launched a payload into space and bring it back down to Earth safely? We're going to look at two types: the shuttle type of a reusable system and the propulsive landing type of reusable system. So the shuttle type you might be more familiar with. The shuttle is, well, when we say shuttle, you probably think of the space shuttle, the big one. It was created it first flew in the early 1980s, and it worked with remarkable efficiency. But it was designed to be almost a fully reusable system, but the final product really wasn't, because it had a gigantic booster that was just detached. Its solid rocket boosters were reused after flight. They landed on parachutes in the ocean, but they were so damaged by the landing that most of the time it took as many as 9 months for a 10,000 person team to refurbish the boosters and the main space shuttle body. So the shuttle works, but it doesn't work extremely well. There have been other designs for the shuttles which have possibly been more effective or more efficient, let's say. Other designs include the Janus vehicle, which is proposed in the 2000s by US aerospace companies, and it would be two space shuttles back to back. One would fly to space, the other would boost it to space, and then just before they reached it, it would detach and fly back to the landing pad, and then to be fueled up again and used as a side booster for another launch. And that would be fully effective. The only cost will be fuel, which is phenomenally good. But Janus never flew. It was too complex and its systems were too prototypey. They weren't real, effectively. And also, shuttle designs have another critical failure, which is, in order to glide back down and land on a runway, you don't just need landing legs or wheels. You need wings. You need some kind of aerodynamic body to lift you there, and you also need a vehicle to get up there which can handle these wings. Because if you think of the space shuttle, it was designed in such a way that the aerodynamic push of the wings would be exactly and perfectly counteracted by the slight tilt of the solid rocket boosters. And it was designed just so. And that cost a lot in terms of research and development and construction time and construction effort. And it was really not a very efficient way to construct a launcher. And in addition to this cost, there is costs of runways. If you have, let's think of the SpaceX landing zones, they're just a very small area of concrete. Well, I say small. They're small relative to the gigantic, almost 5-kilometer long space shuttle landing facility that was built at the Kennedy Space Center in Florida. So space shuttles are not quite as complex or mathematical as the propulsive landing designs, but they are expensive and complex, and they require much more effort to maintain and to think up. So you might think, well, why haven't we been using propulsive landings, the next type, for longer? Well, simply because it's difficult. One of the big reasons is ignitions. I talked about this in the last part, but the amount of times you can turn on a rocket engine is limited. Most of the time, it's limited by the ignition system. So if you want a rocket that can fly up to space, it needs the first ignition for launch, right? Then it will turn its engine off once it's delivered its payload. Then it needs to turn its engine back on to land. So you've got a minimum of 2 times you need to turn the engine on. Now SpaceX, on perhaps the best use of a propulsive landing, is in fact almost the only successful orbital reuse. Their Merlin engine actually has 4 ignitions, and they use a very, very clever method from this. So you'll recall from last time that I mentioned that ignitions were a problem for certain rockets because they didn't use hypergolic fuels. But for the Proton, it actually wasn't that much of an issue because their fuels explode on contact. SpaceX uses kerosene and oxygen, which if you mix them together won't instantaneously explode. You need to set them on fire somehow. So what SpaceX has done is taken the best bit of hypergolic fuels and the best bit of kerosene and liquid oxygen fuels and put them together. They use something called triethylaluminium triethylborane, which are 2 substances, triethylaluminium and triethylborane, TEA and TEB, TTEB, if you want. And as soon as these touch each other, they will explode super violently. And SpaceX uses this to their advantage in a very, very clever way. They pump fuel into their combustion chamber, and then when they want to ignite it, they touch the TEA to the TEB, and it will explode instantaneously. So if they have enough TEA and TEB, they can ignite the engine as many times as they want. Now, this ignition gives off a green flash. So if you ever watch a Falcon 9 or a Falcon Heavy landing video, you'll probably see that just before they light the engines, there's a big greenish, bluish flash from under the engines. And that's the TTEB igniting. So that's one major problem out of the way. But what are the disadvantages of propulsive landing? You've got ignition, of course, which has been solved quite efficiently. But you also have cost. Cost in a different sense, because reusability, you also need aerodynamic structures. Not as much as wings, but if you've seen a Falcon 9, it has grid fins and RCS thrusters on the interstage, and these are heavy and expensive. But if you can create something that works every time, it shouldn't matter how expensive it is, as long as it is reused. If you've seen statistics, I'm going to use the Falcon 9 as an example, often, like time and time again, because it's the go-to method for a propulsive landing system. It is because the Falcon 9, if you've seen the statistics, has I don't actually know the specific details, but it can take 5 tons to orbit more if it's in expendable mode, if they just crash the booster into the ocean. And the grid fins and the propulsive, the RCS, the reaction control system, sorry, should have mentioned that before, they use it to adjust the attitude, the direction of the vehicle as it's coming back down. Their mass just adds up. Now, they're not quite as complex as wings or aeronautical systems or the way that the shuttle launches, but they are a cost to be factored in. So if propulsive landings are to be effectively used instead of sort of a shuttle propulsive system or other types of propulsive systems, then there needs to be an effective lightweight material for vehicle legs and for the vehicles themselves. So as that will develop, it's likely that these things will become more effective and more useful. Right. Now we're going to look at what are other types of propulsive landing systems. I know I've talked a lot about the Falcon 9, but what are other things that can be used for propulsive landing system, and which one works best? For shuttle systems, we had Janus and the Space Transportation System, the Space Shuttle. I've mentioned those, but also the X-37, which is one very, very successful and really quite a clever compromise. It is a small shuttle, much smaller than the Space Shuttle. It's about a person's height, in fact, so it's not very big at all in terms of these rockets. And it's actually launched inside a payload fairing, on top of an Atlas V, usually, or a Delta IV. So it flies to space, and then lands back down on Earth on a runway, which is really quite an effective use of the facilities that were available, because this runway was already there. They didn't have to build it. It existed because of the space shuttle. So this X-37 is really, really efficient, and simply by the fact that it doesn't have to compensate for the aerodynamic roll as it goes up, it just flies up within the payload fairing, so it doesn't affect the aerodynamics of the vehicle at all, which makes it super cheap to develop, which is of course very nice. And the infrastructure was already there on the ground, so the Air Force is in fact currently, as of December 2018, actually flying one of these in orbit around the Earth. And they do secret missions, so I can't tell you what it's about. If I knew. So, other examples of propulsive systems are not just the Falcon 9. We have got lots of companies looking into propulsive systems. The other big one is Blue Origin with their Shepard rocket, I believe. But they use a very high thrust, low mass launching vehicle. So it can't launch much, but it lands very efficiently, and it's much less likely to crash. Of course, it's not very flight proven yet, but I think it will become quite effective as it comes online. But that's my personal opinion. Other vehicles, which have been not quite successful, but there was a proposed mission from the Soviet Union called Zarya, which means dawn, and it was going to be a vehicle which could land itself propulsively. A manned capsule, much like the Soyuz capsule, except rather than land on parachutes, just smash into the Earth, it would land propulsively on hypergolic fuels. And this is another really important reason we should look into propulsive landing systems, because we already use propulsive landing systems. A lot of people will talk about them as if they're like, wow, SpaceX landed a booster, which is, of course, a phenomenal achievement. I'm not going to take that away from them. But this propulsive landing for a first stage is almost like the extension of the propulsive landings that we've been using on Mars for many years now. The Curiosity sky crane was a propulsive landing on Mars. Mars InSight, well, the Schiaparelli lander, crashed, but it was using a form of a propulsive landing system in a combination with parachutes. So this propulsive idea, this reusable system, is going to be very, very important in the future, because we use it everywhere for all sorts of things. And it also brings it back to the fundamentals of rocketry. To recap, those were two sort of design systems, the shuttle type and the propulsive landing type. Each have their strengths and their weaknesses, but it could certainly be argued that one is better than the other. And the shuttle has many more merits than I mentioned. I simply want to point out the propulsive idea because it's what we'll be looking at in the next few parts. We're going to be looking at SpaceX specifically. We're going to look right in on the engines and how they make reusability efficient. Because if you land a rocket, you need to be able to efficiently manage it and efficiently reuse it and refurbish it quickly and easily. So we're going to talk a little bit about their business structure in the next part. So thanks for listening. This one was slightly longer than the previous ones. So thanks. See you then.